Hello everyone and welcome back. So now we've got our second group problem, so let's try it out and see how we do. So what do we have? Well, we have a solid steel rod, okay, and that supports beam AB right here. Now if the stress in the rod must not exceed 30 ksi and the maximum deformation, oh no, it's an optimization problem. The rod must not exceed 0.25 inches, determine the maximum load P that can be supported. And we're going to assume that this is a rigid beam right there, a rigid beam. But usually you can tell when it's a T-beam because those are pretty stiff. So, we're going to find the exact stuff I just said right here. That needs to be edited, but you know what? I'm going to keep on going. So, with this in mind, I'll give you a few minutes, try it out, see if you can solve it, and then come back and tell me how you did. Okay, so first off, the area of the 5/8 inch diameter rod is going to be 0.306796 inches. That's pi over 4 times the diameter squared. Now that helps us, but we need to figure out what the force the rod is feeling is going to be. So if the stress in the rod can't exceed 30 ksi, the maximum force is going to be 9.203 kips. Kip stands for kilopound. So we have our allowable stress, and then we can multiply that by the area to get our allowable force. Now the length of rod 1 is going to be 307.35 inches. So the maximum deformation is 0.25 inches. We can figure out what the strain is going to be. Now we did a little bit of rearranging here. We took our deformation equation, and this time we solved for the force. And when you do that, you realize, aha, do you notice that this is far less than right here? So the stress is not going to be our deciding factor here. Instead, it's going to be the elongation. That's what's going to control this. So the maximum internal force in rod 1 can't exceed 7.237 kips. Anything less than that would be fine. So now we got to figure out what the load P would be. So we're bringing back our free body diagram. We have an angle theta, which is 38.66 degrees. We got that by using tan of theta is equal to 16 feet over 20 feet. Rise of a run. Here's theta. This is 20. This is 16. We figured out the angle. Now we can take our equilibrium equations to figure out what P is going to be. So what we'll probably do is take a sum of the moments around point A, because that gets rid of most of our unknowns, and it leaves only P and F1, which we know. So we do that. We have 20 feet times the vertical component of force 1 minus 8 feet times P. And we solve and get that P has to be less than or equal to 11.3 kips. That's the maximum it can be. So I hope this makes sense to you. Hope you saw how we did this. The big thing with optimization problems is you just don't go all the way through the problem from the beginning. If you do, you're going to be in for a bad time. No, you want to make sure that you check and try to see what's going to be the controlling factor from the beginning if you can, so you don't get to the end of this problem and solve for like 13.3 kips if we'd use the wrong force, and then go all the way through again to see if it should, if it's going to be less. Technically, you'll find out at the end as long as you check out both situations, but it's a lot easier to check earlier than it is to check later. So that's all. Thank you for listening, and I'll see all of you next time. Have a wonderful day. Bye-bye.